Review of Chapter 16. In Chapter 16, we introduced the line integral and the surface integral. First, let's go over line integral. Suppose we have a curve. We can define two types of line integral. First one is a scalar integral. For example, it can give you the mass of a given curve. And the other one is the vector integral. And for the vector integral, you need to specify the direction of the curve, and you need to have a vector field. So in either case, we need to parameterize the curve. Let's say the curve is parameterized by this r as a function of t, and t goes from, say, 0.1 to 0.2. Okay. Then the first one would be f of times the square root of x prime of t squared plus y prime of t squared, and if it's 3D, then also have the z prime of t squared, and then dt. Right? And for the second integral, this one, it would be, let's say this is PQR, and a dot, x prime, y prime, z prime, then dt. So you have a p times x prime, q times y prime, plus r times z prime. Okay? So that's what you do for the vector integral. And by the way, if the vector is regarded as a force, then this is just the work done by the force. There's a special case. If the force field, or say the field itself, is a so-called gradient field, then we can integrate along the curve in a particularly simple way. This turned out to be endpoint and the initial starting point where f is evaluated. So let's say this is A, this is B. So you can just evaluate f at the endpoint minus f evaluated at the starting point. Okay. So if you are given a field, how do we know if it's conservative, right? Or a potential field? Then there's something called Stokes theorem. It tells you that you only need to check one thing. It checks the curl of f. If that equals 0 everywhere, then we can always find out the little f, the potential for this field. And we will go over how to find out its curl. And once you verify that this curl is 0, you can solve for this little f by this. So you have a system, right? Because if that is true, then fx equals p, fy equals q, frt equals r. And then you can find out f by integrate. So if fx equals p, then f is just the integration of p. But be careful, when p is integrated over x, y, and z are constants. So the result will have an arbitrary function, let's say arbitrary function of y and z, because that g wouldn't affect the x derivative. But how do we determine this g? You plug in this f into into the second equation. You take the y derivative, then you'll get something about g, and you will figure out what that is. Then if it's done, that's great. But if it's not, then it still has an extra factor, that an extra constant that is depending on z. Then we will determine what is we'll determine what is this h by plugging this f into the last equation. Then this will tell us what is h. Right, then we will get the result. Then done. Okay, well, I will give you an example. And there is a special form if this is not true. Say the curl is not zero. If the curl is not zero, then we don't know what is the integral along a. Oh, sorry. We can still tell what is the integral along a closed curve. If it's not a closed curve, we cannot tell because it's not a potential field. But if it's closed curve, then we can still find out the line integral through the so-called Stokes theorem. So Stokes theorem says if you integrate an arbitrary field along a closed curve, then the line integral would be the same as the flux of the curl across the surface enclosed by C. Well, then we need to define what is this surface integral. Okay, so that will be our next topic, surface integral. So surface integral also has the scalar part and the vector part. So the vector part would be f dot ds. And just like the curve, you want to integrate, so you have to parameterize this surface. So if we use u and v to parameterize that, instead of just one symbol t, then we will have this one equals f times the norm of ru cross rv du dv. And this is f dot that cross product du dv. Okay, so in principle it can be done in this way, but if you have a very complicated function of u and v, then this cross product would be hard to compute, and then you have to take a norm, right? Make it even harder. So we only need to consider three special cases. First, the surface is given by z as a function of x and y. Then the two integrals can be written in this simple way. So you can just write down this as f times the square root of 1 plus zx squared plus zy squared. Here zx, zy means the derivative, like that. And the flux is f dot, it should be obtained from the cross product, but we know it's just this. And here I have to emphasize that this is the norm of this represents the normal direction of that surface in the positive z direction. If somehow we choose the z direction to be the negative direction, then you have to flip everything by -1. Okay. Second case, let's say it's a cylinder. So if it's on a cylinder of radius r, then you can use cylindrical coordinate. So we will use theta and z to parameterize the surface, and then this will become f times, and the surface element is pretty simple, it's just this. Okay, and how about the vector? Well, then you just need to write down what's normal direction. Well, for cylindrical coordinates, the normal direction is just the horizontal radial direction. So that's cosine theta, sine theta, 0. Then dr, r dr, r d theta dc. Okay. And the third one is the sphere. So suppose your surface is part of a sphere. Then to integrate over the sphere, you can just write down r squared sine phi d phi and d theta, and we'll use phi and theta to parameterize the surface. And how about the vector? Well, just dot the normal direction. And what is the normal direction? Well, normal direction is just in the radial direction, in the 3D radial direction. So you can just say x, y, z divided by r, right? You have to divide by the distance, which is r. And then you have r squared sine phi d theta. Alright, so that's what we do when we have a surface integral. And I have to emphasize one thing. Here we say the cylinder is x squared plus y squared equals r squared, but what if you have something like x squared plus z squared equals r squared? Well, that means we will change y to our like a vertical axis. So your cylinder will be something like that. So you just switch the role of y and z. Well, you can still use d theta, but now it's dy. Okay, that's all. And same thing here. If it's y, the function xz, instead of x as the function instead of z as the function xy, then you will rewrite this as 1 plus y prime x squared plus y prime z squared. Then you have dx dt, right? And this one here will become a little bit more careful. 1 for the y term, and then you have negative y prime x and a negative y prime z, and then you have dx dz, right? So the switch, if it's not z, it's y, then just change y to the role of z. Okay, now let's see examples. The first example is line integral. Let's see. We have a curve. We want to integrate x over that curve, and this curve is given by cosine t, sine t, t, and t is from 0 to pi over 2. And if you remember, this is our helix, from a long time ago. So how do we integrate that? This is a scalar integral, so we would have a square root. And what is x? X is cosine t, and the square root, and what's inside? It's the derivative squared, derivative squared, derivative squared, right? So it's negative sine t squared plus cosine t squared plus derivative dt, and from 0 to pi over 2. And you can see the inside integral is pretty easy. This is 1, so just get root 2 dt, and that's really easy. Square root 2 times sine t. In plugging limits, you'll just get square root 2. So that's your integral. Okay. Now let's see second example. This time let's do a vector integral. So this vector is 2xz 2y plus z x squared plus y. Okay, it's a vector field. And what's C? C is t squared t cubed with t from 0 to 1. Okay, so it's from 0, 0, 0 to 1, 1, 1. And it's a curve, it's not a straight line. Well, of course, we can just do as we suggested in the beginning. Take its plugging this value here, right? You get a function t, and take its derivative xt, x prime, y prime, z prime, dt, right? So you get a big function t, and you just integrate. We should get the correct answer that way. But let's try a different approach. Let's see if this vector field is potential field. Because if it is potential field, we can get the answer very easily, right? And in particular, if your curve is very complicated, this is not very complicated, but if it's something like involving arctangent t, etc., you don't want to take a derivative, right? So it's arctangent is okay, but something complicated, you don't want to deal with the derivative. Then let's check if it's some simple function. A gradient field. Okay, let's take its curl. Alright, what is the curl? I, j, k, partial x, partial y, partial z. And what's in there? It's 2xz, 2y plus z, x squared plus y. Alright, let's take its derivative. Okay, this cross will give you 2x. Sorry, this is y, this is not 2x. This is 1, derivative over y and derivative over z is 1, gone. And this derivative is 2x minus this derivative, which is also 2x. And the last one is this derivative is 0, and that derivative is also 0. So it's 0. That's great. So it is a conservative field. Let's try to find out the f. So fx is 2xz, fy equals 2y plus z, fz equals x squared plus y. So let's find out what is f. Okay. From the first one, we can say, let's integrate. Right? But if you just do that, then you will see if f equals that, then take its y derivative. You don't get that, right? You don't get anything at all. So you have to add an arbitrary constant, but in this case, it's a constant for x, not for y and z. So you can have an arbitrary function y and z. Now let's plug in this f into the second equation. So you take the y derivative. This is nothing. You get gy equals 2y plus z. Alright, what does this mean? It means that we can integrate g. We can integrate to get g. If you want to integrate like that, only z is a constant, right? Y is a variable now, and what is that? That's y squared plus yz, right? So let me. Oh no, not done yet. Just like what we did earlier, you also need to have an arbitrary function of z, because when integrate over y, z is still a constant, right? So let me put them together, plug in there. So you get f equals x square z plus y square plus yz plus h of z. Let's plug into the last equation. Fz. Let's take a derivative. It's x squared plus y plus h prime. Alright, let's see what it should be. It should be just that, x squared plus y. So, what does that mean? It means h prime equals 0. So you can just set h z to be a 0, or arbitrary constant. Why not just set to be 0? So that's it. This is your f. So we found the f. And once you know f, it's really easy, because there's one. It's just equal to f of the end. What is the end? The end is 1, 1, 1, and the start is 0, 0, 0. So f1, 1, 1 minus f0, 0, 0. What is f1, 1, 1? I'm plugging x, y, z equals 1 here. You get 1 plus 1 plus 1 equals 3. And then 0, 0, 0 will give you 0, so that's the answer. Alright, so this example shows you that if you can verify a field is conservative, then the line integral is really simple. Okay, that's it for the line integral. Now move on to the surface integral. First, let's do scalar. And how about this? Let's find out the surface area of this object. This is x equals y squared plus z squared. So it's a paraboloid, but in the x direction, right? This is x. And this is x equals 2. So you cut it at x equals 2. Then get a 3D domain. And let's find out the surface area. The total surface area. Right? So obviously there are two parts, S1 and S2. And S2 is easy. What's the area of S2? You can see it's a circle, but the radius is not 1. What is the circle? The circle is y squared plus z squared equals 2. So the radius actually is root 2. So the square is still 2. So that's your area. Okay? Be careful, it's not 4 pi. It's 2 pi. Now let's find out the surface area of this paraboloid. How do we do that? So the area of let's say, the area of S1. Okay. So that would be the integration. Well, how do you parameterize that? This is not a sphere, not a cylinder. So we have to regard this as a surface defined by this equation. So we should use dy dz as our variable, right? Then what's inside here? It's 1 plus x prime y squared plus x prime z squared, right? And we'll figure out the limits later. Let's see what's inside the square root. Take a derivative, you get 2y and 2z. So it's 4y squared plus 4z squared and dy dz. Okay, what is this domain? The domain is just this, right? Or actually, it's project onto yz plane. It's like that. It's the same thing. It means y squared plus z squared is less than or equal to 2. Okay, so now we switch to polar coordinates. We don't switch it here because when you write down polar coordinates, you don't know what is this guy, right? So we use y and z at this stage. Then we switch to polar coordinates after we write down the integral. Okay. Right, then let's say r d theta, and let's say y equals cosine theta, sorry, r cosine theta, and z equals r sine theta, right? So the theta is 0 to pi, and r is from 0 to root 2. No, it's not 2, it's root 2. And what's inside? 1 plus 4y squared plus z squared is just r squared. And that's it, right? Just this integral. Okay, can we do that? Well, it's kind of easy. For theta part, it's just 2 pi, right? And for r, it's you can see, you can call this u, right? Then this is a du over 8. So and u go from 1, plugging 0, and plugging root 2, you get 2 times 4, 8 plus 1 to 9. So you get 1 to 9 square root of u du over 8, like that, right? So what is this? This is 2 pi and times 1/8, and u to the 3/2 times 2/3, and then from 1 to 9. Right, let's do some cancellation. This and this and this, you get 2. So you get pi over 6, then 9 to the 3/2 is 3 cubed, 21 minus 1. That's 13 over 3 pi. Right, then don't forget you also need to add this part. Right, so the total area equals 13 over 3 pi plus 2 pi, and that's 19 over 3 pi. Okay, that completes our example. Our last example would be the surface integral with a vector field. And this time, let's do a sphere. X, Z, Y, and this S is, let's see, what is this S? S is x squared plus y squared plus z squared equals 1. Okay, really easy. It's just a unit sphere. But let's make it a little bit harder. So let's say it's on the top half of that. So we just cut off the bottom half. So it's a top half. And let's say it's let's make it two surfaces. Okay, so the top is S1 and the bottom is S2. And what is S2? S2 is just the circle on the XY plane. Okay. Well, then when we say ds as a vector, we have to say what is the normal direction, right? So let's say this is the outward direction. All right, this is n, this is n. So you notice that for the S1, it's upward. For S2, it's downward. Okay. So let's find our integral. So first we integrate over S1. Let's see what it is. X, Z, Y. All right, do you remember what do we do for the surface? It's spherical. So we would use r squared sine phi d theta. Right? We use phi and theta. And what is this? This is a normal direction, right? This n here, which is x, y, z over r. And all of this r is just 1, so it's gone. So let's see, what do we get? We take the dot product. You get x squared plus yz and yz again, 2yz, and then have sine phi d theta. And this is upper half, so theta is 0 to 2 pi, and phi is 0 to pi over 2. Okay, how do we integrate? We have to write down x, y, z all in terms of theta and phi. Right, what is x? Oh, x is sine phi cosine theta and square it, and y is sine phi sine theta, and z is cosine phi. Okay, all of this times sine phi d phi d theta. Okay, and although it looks complicated, but notice that this is the theta part, and that is the theta part. So if you integrate this times that, you see the sine theta part will give you, integration will get negative cosine theta, right? Then you plug in limits, what do you get? 0. So that's gone. So we only need to worry about the first part, right? Then you have sine theta sine phi cubed 0 to pi over 2 times cosine theta squared, right? So what is that? Again, so you have to move one of them there, so you get sine square phi and d of negative cosine phi, right? 0 to pi over 2, and this you write down this as a double angle formula. Alright, so what do we have now? You write down this as a 1 minus cosine phi square, right? Then switch, this one move here, so it becomes cosine phi square minus 1, right? So now you do the u substitution. This is u square minus 1 du, and the u go from 1 to 0, right? Cosine 0 is 1. And this one is theta plus sine 2 theta over 2, and plug in the limits. You will see that it's gone, so it's just a pi. Right, that is just pi. And how about this? This is u cubed over 3 minus u from 0 to 1. And 0 gives you nothing, 1 gives you 1/3 minus 1, which is negative 2/3, and then becomes 2/3 times pi. Okay, almost done. The other surface is the bottom one. Right? What is the bottom surface? It's just a circle on xy plane. And so let me just do it here because it's really simple. S2 x z y, and what is the normal direction? It's negative z direction, so it's this, right? It's pointing downward. Then you just write down, say, dx dy, right? Because it's a plane, so we don't need to use some fancy coordinates, just xy. Then you see this time that is negative y, so it's integration over unit circle with negative y. And what is that? That's just x squared plus y squared is less than or equal to 1. Then you have negative y times dx dy. Okay, this is a circle, so let's just use spherical. So this is negative r sine theta, and r dr d theta, and r is from 0 to 1, and theta is from 0 to 2 pi. And you can see sine theta times d theta would give you cosine theta from 0 to pi, and that's once again 0. So that is 0, right? So you see the symmetry really helps. So what's the total? Just 2/3 pi. So the total integral, closed. Okay, all right. And just to make it more interesting, there is something called divergence theorem, which says this quantity is the same as the triple integral of the divergence of f integrated over this domain. So what is the divergence? F equals, double check, it's what is that? Okay, x, z, y. X, z, y. So divergence takes x derivative, sorry, then get 1, then y derivative is nothing, y derivative is nothing, so that's 1. Well, that means it's just the volume, right? And what is the volume? Well, it's a half sphere, and so it's half of 4/3 pi r cubed, and r is 1, so it's just that, and then you have that. Well, that agrees with what we had. Okay, so you can see this confirms the divergence theorem. Alright, I think that's it for the review, and just to do this and also do your homework, and we will have the exam next week. Not next week, just in 2 days. Okay. Bye.